My name Chaitra Sajjan. Class BSc first semester. Subject chemistry. Topic name derivation of integration rate equation for zero order reaction, both for equal and unequal concentration of a reactant. Derivation of integration rate equation for zero order reaction, both equal and unequal concentration of a reactant. Introduction. Zero order reaction about integration rate equation for a zero order reaction with graph. Derivation of a zero order reaction, equal and unequal initially concentration. Reference. Zero order reaction. If the rate of the reaction is dependent of initially concentration, then it is called as a zero order reaction. That is, R is directly proportional to C naught or R is equal to Kg naught. Example, H2 plus Cl2 to form 2HCl. R is equal to K bracket H2 naught and Cl2 naught. Therefore, N is equal to 0. The integrated rate equation for zero order reaction. Reactant to product is a derivation by setting the rate equal to the constant K. Since rate is equal to K, R naught is equal to K. R is a concentration at a time T and R naught is the initial concentration. The rate constant is K is equal to R naught minus R divided by T. It is a integration rate equation for a zero order reaction graph. Derivation of a zero order reaction. First step is rate expression. For the reaction, reactant to product, the rate is independent of a reaction of a reactant concentration. Rate is equal to minus R minus dr divided by dt is equal to kr naught. Since r naught is equal to 1, this simplifies to minus dr divided by dt is equal to k. Next step is rearrange the integration. Rearrange the equation to square root variables. dr is equal to minus k dt. Integrate both sides. Integrate dr is equal to minus integrate k dt. R is equal to minus kt plus c, where c is the integration. Third step is find the integration constant. At time t is equal to 0, the concentration R is equal to R naught. R naught is equal to minus K0 plus C is equal to R naught. Fourth step is final integrated rate equation. Substitute C back into the equation. R is equal to R naught minus KT. Alternate for the amount of reactant consumed X in a time T. X is equal to KT or K is equal to X divided by T, where X is equal to R naught minus R. Next one is equal and unequal initially concentration. Zero order reaction kinetics are typically defined by single reactant concentration, but if considering a reaction A plus B is equal to P that have as a zero order reaction. Example, catalyze reaction where concentration of a reactant is a high. Equal concentration R naught is equal to B naught. The concentration rate in a constant initially either reaction is fully consumed, the equally hold as X is equal to KT. And unequal concentration A naught does not equal to B naught. The reaction rate is still independent of a concentration determined by the rate constant and the limiting reactant. The same formula x is equal to kt applies where R represents the reduction in the concentration, the limiting reactant. Initially, the reactant is consumed. It is a derivation of a equal initial concentration. The rate of reaction is proportional to the square of the concentration. Rate is equal to dx by dt is equal to k bracket a minus x whole square. Rearrange the square root concentration and time term. Dx divided by bracket a minus x whole square is equal to k dt. Integrate both sides. Integrate 0 to x. Dx divided by a minus x whole square is equal to integrate 0 to 1 k dt. Result 1 divided by a minus x minus 1 divided by a is equal to kt. It is an unequal integration concentration derivation. Rate is equal to dx divided by dt is equal to k a minus x bracket a minus x b minus x. Dx divided by a minus x bracket b minus x is equal to k dt. 1 divided by a minus b. Integrate dx divided by b minus x minus integrate dx divided by a minus x is equal to integrate k dt. X is equal to 0 or x is equal to x and t is equal to 0 to t to t. 1 divided by a minus b log b minus b bracket a minus x divided by a bracket b minus x is equal to k dt kt. Reference Chemistry 2 Dr. Vinayak M. Nayak Physical Chemistry V.P. Sharma. Thank you.